Hello, my name is Radu, and this is the screencast for my third-year project named Integrating the RoTRA Highway Code Tool with CARLA Autonomous Vehicle Simulation. This project contains two main components, RoTRA and CARLA. We'll discuss in more detail about them later in this video. But first, the goal of the project is to engineer a way between RoTRA and CARLA such that whenever a violation occurs in CARLA, RoTRA will be there to flag it up. The purpose of this is that whenever a violation or a mistake occurs in CARLA, RoTRA will be there to intervene, giving the objectively correct instruction in that specific situation. The greater purpose of this is to make the AV environment a little bit safer. Now, before we delve into this project, let's talk a bit about how an AV works. An AV works by employing a variety of sensors, cameras, radar, and other technologies to perceive the world around it without human intervention. A good example of a sensor would be LiDAR, or light detection and ranging. How LiDAR works is by measuring the time it takes for laser pulses to bounce back after hitting an object. Another familiar example would be ultrasonic sensors that employ high-frequency sound waves, otherwise known as parking sensors. Thank you for watching. No, that's later in the video. Anyways, come with me home so I can show you more on my laptop. Now that we're here, let's take a closer look at the components of this dissertation. First of all, we have RoTRA, which is one of the two main components, the other one being CARLA. RoTRA, or Road Traffic Rule Advisor, is a type of BDI system that employs all the rules from the UK Highway Code that are directed towards a driving vehicle. Why is that? Well, because the purpose of this project is to improve an already existing AV. All the rules that would be directed towards cyclists or pedestrians or other entities are not important to us. So, a BDI system, what is it? BDI stands for belief, desire, intention. And it's a type of system that, given a situation, it will always respond with the appropriate outcome. In our case, given a specific scenario, the BDI system RoTRA will give us the expected correct action given its UK Highway Code legislation. For example, if we look at rule number 175, we can see a more detailed view of what it is composed of. First, it is the name, then there is the situation that we find ourselves in our case standard. There is also an emergency situations when emergency vehicles, ambulances, police cars are around us, but this is not the case right now. Then we have the three main components of the BDI. The belief, light red, which means that the light ahead of us is red, obviously. Then the desire, which is approaching traffic light, which obviously again states that the car is traveling in the direction of the red light. And then the intention, which is in itself composed on two components. There is either a should or a must, which will specify the importance of this rule to be applied. And then it is the actual intention, stop at white line, which stops the car at the white line. Very good. Now that we've talked about RoTRA, let's turn our attention to something a bit more flashy, CARLA. CARLA is the second main component of this integration. It is an open source autonomous driving simulator developed by Intel cars with the purpose of simulating real-life scenarios for training autonomous vehicles. The autonomous vehicles in CARLA have the same means of detection as their real-life counterparts. They have the same sensors to detect objects around them, such as LiDAR or radar. These sensors, coupled with a few maps that CARLA has, can help the user place their AV in the exact specific scenario that they wish for it to be trained. Another different parameter that can be tweaked is the weather. CARLA employs various different weather scenarios ranging from the default sunny day to the more extreme thunderstorms. This, coupled with various junctions that can be found in its maps, provide a very comprehensive array of situations for an AV to be tested in. Here are a few examples of them. Right, now that I've explained both of the components, it's time to take a closer look into how they work. I am using a client-server architecture for this, where CARLA will be the client and RoTRA will be the server. Connecting them would be an agent. The agent module consists of 4 main classes: CARLA SDK, Observer, RoTRA Client, and Action Mapper. Let's take a look at the easier ones first. CARLA SDK is just a means for our program to communicate with CARLA GUI. CARLA is just the output of our code. It is not actually what we've implemented. Then we have the RoTRA client. Again, this class is fairly straightforward. It just sends our information towards RoTRA so that we can expect an outcome back. Remember, RoTRA is our server. We need to feed it the information, in this case the belief and the desire, and it will return the intention. Now, let's talk about the other 2 classes, Action Mapper and World Observer. World Observer is just a class that takes information from CARLA SDK and transforms it into a compatible format for Prolog. It oversights the whole world, having information on everything that we need. For example, if we take a look at the code here, we can see class Traffic Light Observer. Observer class is composed of a lot of those subclasses that contain observance for different types of purposes. For example, a traffic light observer monitors the state of the traffic lights. After the information has been taken from CARLA SDK, it is transformed and sent to Prolog in a belief desire format, and it awaits the intention. When the intention is returned, it is under the shape of a string. So we need to manipulate that string and to implement the actual functionality of the string. Depending on what RoTRA outputted, we assign it a priority, low, medium, high. Remember that we use the should or must specifiers in RoTRA. This is where the priority is assigned. Those with must have a high or medium priority depending on the rule. Given the rule, given that it is in a string format, we need to transform it into actual controls. For example, all the basic controls are implemented in class Action Mapper. One would be stop, slow down, turn left, right, and so on and so forth. They represent all the basic information that we need to feed CARLA to take control of a vehicle in an emergency. A specific example, stop, which means an emergency stop, would have a throttle control of 0 and a brake control of 1, which means maximum brake pressure. Also, priority is high because it represents a controlled emergency stop. Now, let's take a look at how a very simple example works. In front of me, I have the CARLA environment already generated. I have also created a very simple example of how this works. How this is going to work is that the car will come from this road, from in front of us, will go over this bend and will detect that red light. If everything goes according to plan, then an output of red light detected should be written here. Let's run this. Everything is initializing. It will take a second. The camera will move away because it has to regenerate the location every time. But no problem. The spawn point is fixed. So we just move the camera to follow the car. So you see the car over there. If we go back to the code, you see red light detected, and then the car successfully stops at the red light. In order to accurately test this and to make it work in a variety of scenarios, I had to test it in a multitude of locations with various conditions of weather and various junctions. I will now show you a few of them.